Good morning. Today we would like to dive into the Kalman filter and the extended Kalman filter as a concrete realization of a recursive based filter. And we will do so in rather, hopefully, at least intuitive way. So we are not going through the whole derivations, but I want to give you an idea what is behind the Kalman filter and what are key steps to reach it, why it has the form that it has, so that you get an idea what the properties of the Kalman filter are and how you can perform state estimation with it. So the Kalman filter is a recursive based filter, and it's a special filter because it requires the world to be Gaussian. That means every involved probability distribution is supposed to be a Gaussian distribution, and it assumes linear models. And in this case, for the Gaussian linear case, it is actually the optimal filter, so the optimal approach that you can do. So in this case, it is also equivalent to a least squares approach, as long as everything is Gaussian and all the models are linear. And the least squares approach, as well as the Kalman filter, will provide the same result. The way the result is computed, however, is done in a different way. So the Kalman filter follows the idea of a recursive based filter and performs this type of recursive state estimation. That means we're taking our current belief, we're taking the current information that we have from our control commands and from our observations, and turn the previous belief into the new belief, so that we turn the belief from time t-1 to time t. And so we are always updating the belief, taking the most recent observation and control command into account, and don't do everything kind of as a batch operation. And for taking into account the control commands, we perform the so-called prediction step. So we predict what's going to happen given the control information that we have. And the second step, according to the base filter, is the correction step, which takes into account the observation in order to correct for potential mistakes that we have done in the prediction step. So we perform a prediction, then we correct it, then we perform a prediction, and then we correct it again. That's kind of the key idea behind the Kalman filter. So let's start with a small Kalman filter example, just as an illustration how that looks like. So consider you're on a boat and you're driving near the coast, and you, let's say, have a rough idea where you are, which is indicated here by this black circle. And so you're navigating, and let's say you you try to keep the ship in a certain direction and try to follow for a certain amount of time that direction. So you are actually moving forward. And let's say you get a new estimate and you say, I am probably here where that cross is. And this is kind of what is in the Kalman filter the prediction step. So you're performing your action and you predict what's going to happen, where you are with your boat. And then you look to the coastline and see if you find any lighthouse. And let's say you're in the lucky situation that you see a lighthouse, like get your lighthouse observation over here, and this allows you to determine where you are, at least to some degree. So just one lighthouse observation may not be sufficient, but at least it allows you to estimate your orientation well, and multiple lighthouse observation will tell you more about your pose. But assume we have some observation right now which tells me something about my position. And then we can perform the correction based on the prediction. So this is where we predict where we are. Then we have our lighthouse observation, which is here illustrated by this dashed line. So based on our observation, we know that we are, let's say, somewhere here on that dashed line. And then we can perform the new state estimate as a combination of where we are predicting where we are, here shown in green, and the predicted one, which is a black one, which gives me the joint estimate here shown in red. So this is kind of the belief combining the prediction and the correction. So to sum up, we were somewhere over here. We are making a prediction, estimating where a ship is without any observation, any prior information. Then we get an observation, which tells me, which I'm seeing the lighthouse over here, and the observation tells me I'm here at that green cross. And then what the Kalman filter basically does, it computes a weighted sum of the prediction where you think you went to, what your observation tells you, and that's kind of the belief here shown in red. And the Kalman filter basically computes a weighted sum, taking into account how certain you are about your prediction and how certain you are about your observation. And basically trades off these uncertainties and then can trust the observation more or can trust the prediction more, depending on the current estimates. And this is kind of a very simple illustration about the Kalman filter. Okay, so let's have a quick look to the base filter and see how the Kalman filter and the base filter relate. So also the base filter, it was the tool that we derived for recursive state estimation. It is a prediction step and a correction step. And the prediction step is shown over here. So we are starting with our previous belief and we are integrating about all states, or in this case, positions or poses, where the system possibly is at the previous point in time. So this is shown by this integral, and we're integrating about the position at the previous point in time. And then I'm multiplying this belief with the so-called motion model or control model. So where am I at time t, given I know where I was at time t minus 1 and which motion has been executed, and I'm integrating over all those states. So what happens there mathematically is a convolution of two probability distributions. And then in the correction step, I have my predicted belief, my prediction, and I have my observation information, my observation model, which is shown over here, and this was just a normalization constant. And then I'm basically multiplying those two probability distributions. So the one from the prediction and the one, the observation model, so that I'm actually correcting the prediction. And that's kind of the general framework of the recursive base filter, and also the Kalman filter exactly follows those steps. So the Kalman filter, as I said, is a realization of the base filter. It assumes that everything is Gaussian and that we only have linear models. And in this example, it is the optimal estimator. Optimal means here statistically optimal, so you can't do better than the Kalman filter. So as long as all your models are linear and your probability distributions are Gaussian, there's no need to investigate anything else than the Kalman filter, or maybe least squares approach, which is equivalent in this case. But you don't have to look for other state estimation techniques because you basically can't do better in terms of your estimation result. And again, the key thing is everything is Gaussian and everything, all the involved models are actually linear. And now what we want to do is we want to dive a bit more into the details on how the Kalman filter is set up and how it looks like and what do we need to do in order to derive the basic Kalman filter equations. Again, we are not going to do the derivations here. This is something that you can do on your own. I'm trying to give you an idea what happens or what tools you may need, and we'll show maybe some properties of the Kalman filter here, but then more want to discuss what we can do with the Kalman filter, what are important things to consider, and give you kind of visual, intuitive explanation for what happens in the Kalman filter. Okay, so the question is, if everything is Gaussian, we start with a Gaussian belief. The question is, how do we update this Gaussian belief based on my motions and my observations? And that's kind of one step that the Kalman filter is executing. So what we need in order to derive those equations, so you can see this, can do these derivations from a probabilistic point of view, but you can also do the same way from a linear algebra point of view. And the two key operations that are typically needed in most of the derivations is marginalization and conditioning of Gaussian distributions. And just as a short reminder, if you have a probability distribution over two variables or two subsets of variables, xa and xb, and this probability distribution is a Gaussian distribution, a normal, then what we have is that the marginal distributions are also Gaussians. So if you, for example, integrate away this part xb, that only p of xa remains, this will be a Gaussian distribution, and the same way the other way around, that p of xb also will be a Gaussian distribution if I marginalize out a. And the same holds for the conditional distributions. So p of xa given xb, so assuming I know xb, the probability distribution about xa will be a normal distribution again, and exactly in the same way, the other way around, p of xb given xa is also a Gaussian distribution. So this is a key property that we are going to exploit if we derive the Kalman filter. So we will be mainly relying on computing marginals and conditionals and also convolutions. And the important thing is here that all those distributions stay Gaussian distributions, to not violate the assumption that everything stays Gaussian, because in the next step of the Kalman filter, we will again require our distributions to be Gaussian so that all operations hold. We're not going to dive into the details how the conditional and the marginal look like. Marginal is computed very easily. The conditional is slightly more complicated, but you typically need end up with the sure complement being executed in order to come up with this conditional. But these are the tools that you need if you want to perform the derivation of the Kalman filter from scratch. The next thing we want to look into is our linear models for the motion as well as for the observation. What does this mean, a linear model? So a linear model means that both models can be expressed through a linear function, here shown in this setup. And so we are having a variable, this can be a multidimensional variable, so I'm having matrix AX and some constant term. And the key thing is that if we take such a linear function and we transform a Gaussian through this linear function, it stays a Gaussian distribution. And again, this is an important property, because if we want to take our current belief that is Gaussian and we want to combine it with a Gaussian model like an observation or a prediction, we need to make sure that the result that we get out is actually also a Gaussian distribution. And this function may add additional uncertainty to the process, like the motion model. So I start with a Gaussian belief, I perform my motion. This is likely to increase the uncertainty that I have, but through this linear model and my Gaussian noise associated to that, I can ensure that everything stays Gaussian. And so this is something that these models that the Kalman filter actually exploits. So in the Kalman filter, we assume to have zero mean Gaussian noise and this linear models. So this is basically the step for the prediction, for the prediction step, yes, for the control commands that we say the current state xt equals a matrix AT times the previous state, plus a matrix BT multiplied with the control commands, which takes into account the changes of the state given the control. So this part basically says how does the state changes without doing anything, and this is kind of what is the additive term that is added to that state based on the control command, and then we have some Gaussian error over here. And similarly for the observation, so what we are basically doing here, we are computing a predicted observation based on the state. So we have this matrix CT, which maps from the space of states into the space of observations. And if I multiply this matrix C with the current state xt, it basically tells us what we should observe. And this is what we often call the predicted observation. So we take the matrix C, we multiply the variable x to it, and then it tells us what our predicted observation is going to be. And this is also associated with some Gaussian noise term. So these will be the linear models that are involved in the Kalman filter. So let's dive a little bit into the details and explain the individual components here. So we start with this matrix A. A is an n by n matrix where n is the dimensionality of my state vector, and it tells us how the state evolves from time t-1 to time t if we don't apply any controls or have any noise or errors associated with it. So AT basically tells us how does a state evolve. So in the most trivial case, this AT may be an identity matrix, because if you say, if I don't do anything, my state shouldn't change. In this case, AT is an identity matrix, and then turns the belief about the state at time t into the previous state, xt-1, plus the change that comes from the control command. But I may have a reason that this is not an identity matrix, that the state evolves even if I don't do anything. If you think, for example, about a vehicle you're driving and you're pushing the gas pedal, and even if you don't push the gas pedal, you still have some remaining, let's say, constant velocity, which changes the state, the position of your vehicle over time. So this information may then be encoded in your matrix AT. Another alternative is if you have external factors like a UAV and you have a blowing wind. So even if you don't control the wind itself, it's an external factor which is in there and which could be integrated into this matrix AT so that the wind generates some drift for your UAV, for example. And then the second important part is this matrix BT. Matrix BT is an n by L matrix where n is the dimensionality of the state space and L is the dimensionality of your control command, so of your UT. And it basically tells you how UT changes the state. So it tells me if I take a odometry command or another control command or some velocities that I give to my system, how do those velocities change the state of my system? So it's a mapping from the space of control commands into the state space. And therefore, and there's an additive term, so this is something that we add in the previous model to our previous state, or the how the previous state evolves, plus this term BT. So it's an additive term which tells you how much do I increase or decrease every individual dimension of my state vector based on the control commands. And this is what we need for the prediction step. And then we have for the correction step, we need this matrix T, which is in K by N matrix. So K is the dimensionality of my observation and N is the dimensionality of my state space. And it basically tells me how I can map the current state into an observation. And that means is what I'm going to observe, or what do I expect to observe given that I'm in the state xt. So if I'm xt and I want to get an observation, what I'm expecting to observe, and this is what this matrix CT tells us. So it maps from the state space, the n-dimensional state space, xt, into the space of observation, which is here referred to as zt. And then what we have for both models, we have random variables representing Gaussian noise, and this is zero mean Gaussian noise independent of each other, and this is typically referred to or expressed with two covariance matrices, RT and QT, and it depends a little bit on the community you're coming from. Sometimes RT is the noise for the control commands, sometimes for the observation, and QT the other way around. So I'm using here RT as the noise for the motion and QT as the noise for the controls. This is in line with the probabilistic robotics book, for example. A large body of literature outside that community actually uses it the other way around. So be a bit careful if you compare that with some other material. Make sure you're using the right uncertainties over here. Okay, so let's have a look to what it means linear model. So given that we are in the state of probability distributions, so we need to estimate the probability distribution accordingly. So what does it mean to have a linear motion model with Gaussian noise? So if we write it down, what means having P of xt given ut and xt minus 1? That means I know where I've been before, I know the control command that I'm executing, what the probability distribution, where I'm ending up. And this must be a Gaussian distribution because everything in the Kalman filter is Gaussian. So how does it look like? Okay, obviously it is a Gaussian distribution, and we should make sure that we know where we have been before, and the question is where are we going to end up when we execute the control command ut. And this is again where our linear model comes into the game. So our matrix AT, our matrix BT. So we can say, okay, how does xt changes, xt minus 1 changes if we move to xt? That was A times xt minus 1 plus b times ut. And this gives me a new prediction where I'm going to be. So this will be the mean of my Gaussian distribution. So this specifies the mean of that Gaussian distribution. So I'm basically looking how far am I away from the mean. And then I need to divide this taking into account the uncertainty of my motion. So in this case, the covariance matrix RT as the uncertainty associated to this. So that I can specify what the probability distribution of where I'm ending up, given I know where I started and the control command actually have executed. So then we can actually write down a standard Gaussian distribution So this is constant factor over here, and this is my exponent. What I can see in here, this is exactly the part of the linear motion model. So this is basically the negative mean, so where I'm expecting to be based on the control command that I executed. And of xt minus this term, minus the mean, so it's basically how far am I away from the mean. Same expression pops up over here, and then we divide that by the covariance matrix, or the inverse of the, multiplied with the inverse of the covariance matrix that encodes the uncertainty of that motion model. So how much noise do I add to the motion? And so this is then my probability distribution, which is Gaussian and incorporates the linear model in order to tell me how the system advances from t minus 1 to t. And I can do the same exercise for the observation. So how does the observation look like? So again, we assume we have our linear model and everything is Gaussian. So again, we need to compute our predicted observation and then see how far are we away with our real observation from that predicted observation. So the predicted observation takes into account the current state, ct, so that was xt, sorry, and I compute that by taking this matrix ct and multiplying ct with xt. So ct times xt gives me the predicted observation, the mean observation, what I'm expected to observe, and then I take into account what's the difference between what I'm expecting to observe and what I'm observing in reality, and then I have a Gaussian distribution over that difference with the uncertainty of my observation. So very similar as before, we have our constant factor over here, which now just uses the uncertainty of the observation, not the uncertainty of the control command. And then we have here our negative mean, which is ct times xt, so what I'm expecting to observe. And I'm basically computing the difference between what I'm actually observing and what I'm expecting to observe, and then take the uncertainty of that observation into account. So this is again my Gaussian distribution as the model for my observation, taking into account that everything is linear over here. Okay, so that means we have shown that the motion and the observations are linear Gaussian models. That means we end up having Gaussian distributions, and the previous state is exploited, or the current state is exploited, the predicted state, in a linear fashion. And everything stays Gaussian, or is Gaussian in these models. So the next thing that we need to do is we need to show that everything also stays Gaussian if we compute our updates. And for that, we need to go back to the recursive based filter equations. So one of the equations tells me that the current belief is the predicted belief times my observation, and this was just a normalization constant, making sure that the integral ends up being 1 over all possible states. So this part over here is something that we just derived. This was the observation model, sorry. And so we know that this is the Gaussian distribution because we just have written it down. And then we have our predicted belief. And the question is, what is our predicted belief? Was this a Gaussian? Is it not a Gaussian? Assuming that it is a Gaussian, if you assume that the predicted belief is a Gaussian, then we know that the result is a Gaussian because a product of two Gaussian distribution again ends up being a Gaussian. So as the product of two Gaussians is a Gaussian again, the only thing we need to show is that the predicted belief is a Gaussian distribution. So if the predicted belief is a Gaussian distribution, it turns out that the corrected belief also will be a Gaussian distribution, because the only thing that happens is that I'm multiplying this Gaussian with another Gaussian, and that will lead to a Gaussian distribution again. So the next thing we need to inspect is this part over here, the predicted belief. Is this a Gaussian, yes or no? Okay, so let's have a look into the definition. So I have my predicted belief, which was the integral over all previous states, the previous belief times my motion model. So we just defined that this term, the motion model, is a Gaussian distribution, right? So that's the thing that we just did, just have written it down how it looks like explicitly. So we know that this is a Gaussian distribution. And about our previous belief, we can also assume it to be a Gaussian distribution. Because we said we start up with an initial belief. The initial belief is a Gaussian distribution. And then if this is Gaussian and the whole update steps involve operations that everything stays Gaussian, the next belief will also be Gaussian. So the next belief is recursively fed into that. So the only thing that I need to show is basically that I start with a Gaussian, my initial belief, the constraint that I had, and then that assuming it is Gaussian, if the result is also Gaussian, as a result is plugged into it again, it will stay Gaussian, as it is a recursive expression. It's similar to a proof by induction where you say we have our initial state that we describe, which says it's Gaussian, and then we need to make sure that in the induction going from n to n plus 1, this is our time state going from t to t plus 1, that everything stays a Gaussian distribution. And that's actually what we are going to do here. So the question is this sufficient that these two are Gaussian distributions, but I still have this integral over that variable in there? So is that sufficient so that these two are Gaussian so that this term also is a Gaussian distribution? And that's a good question. But what it actually is, if you inspect that equation further, then you see that this is actually a convolution of two functions. So we are convolving these functions over here. And the convolution of two Gaussians is, again, a Gaussian distribution. And as a result of this, the overall term will stay a Gaussian distribution. Maybe you haven't seen that yet, so I can go very quickly through the proof that this is the case, that in this example here, if those two distributions are Gaussian, our resulting belief will stay a Gaussian. We just can go quickly over it. We start with our predicted belief, just writing down the definition, and then just filling the individual two probability distributions based on what we had before, based on the definitions. So this is what we had showed before. This is kind of our motion model. I'm just kind of ignoring here the constant terms, so they are all in normalization constant over here. And then I have here the product of two exponential functions, one of my motion model, and the other one is just the Gaussian about our previous belief. So the recursive belief, so this term over here. Okay, and what I can do, I can actually combine those exponential functions. So what we can do is we can formulate a new Gaussian distribution in here over combining these two exponential functions. So I can say this can be expressed as the exponent about some function Lt. And the question is, how do these things need to be combined? They need to combine the following way, as the sum of those two exponents over here. So you have two exponential functions, to multiply them, you can combine them into one by just adding up the individual terms here in the exponential function. And then we can actually split that term Lt up into two terms. One term Lt that depends on xt minus 1 and xt, and another part which only depends on xt. And then I can actually rewrite this integral into two parts, or I can move one part of the expression out of it, namely the part that only depends on xt. And then I have the integral over xt minus 1 sitting over here. So this is a Gaussian distribution. It can be expressed again as a Gaussian distribution. It's just those terms of the exponent which only depend on the variable xt and don't take into account the variable xt minus 1. And then this is basically a marginalization operation of the variable xt minus 1 also being a Gaussian, and the marginalization of a Gaussian distribution, as we said before, stays a Gaussian distribution. So this will turn then the overall term into a product of two Gaussian distributions, which again is Gaussian. If you want to go a bit more into the details and go step by step through this proof, I recommend the probabilistic robotics book. Chapter 3.2 will actually guide you exactly through that process. So as a result of this, the predicted belief is also a Gaussian distribution. So that finally we can say, this is a Gaussian distribution, this is a Gaussian distribution, the integral over it is a Gaussian distribution. As a result of this, my predicted belief is a Gaussian distribution. So this is Gaussian, multiplied with another Gaussian distribution. This is just a normalization constant, so we don't care about it. And so as a result of this, this will be a Gaussian distribution. So as long as we are living in this linear world and the individual models are Gaussian, everything will stay Gaussian. So from the beginning to the end, we'll never leave the Gaussian world. And that's important, an important property, so that we can actually update our belief at every point in time, and can execute the steps also in the future when the new observation and the new controls come in. Because if we would leave the Gaussian world at some point, that would mean that we don't have a Gaussian input anymore for the next state, and then the whole thing would actually break. So it's important that we live in this all the time in this Gaussian world, so that we can recursively apply our update rules and evolve the state from time t-1 to the time t. So what we have learned so far is that we use linear models for the observation and the control commands, which we actually have written down. This for the motion command, it's an xt predicted is at times xt-1. So how does the state change if I don't do anything? Plus bt times ut. How does the control changes our state? Plus some Gaussian noise. And for the observation, we can compute a predicted observation in linear case by saying zt, the predicted observation, is the matrix ct multiplied with the current state xt, saying which observation would the system generate if we are currently in xt. That's what this function ct tells us, plus some Gaussian noise. So if we have that, everything is Gaussian, then we will stay continuously in this Gaussian world. And have basically shown that everything stays Gaussian as long as we're living in this Gaussian, or everything is Gaussian and linear, so that all the steps are Gaussian distributions all the time. So the only thing we need to do, we need to maintain Gaussian distributions in the overall step of the Kalman filter. So how do we represent our Gaussian distributions? Gaussian distributions can be easily represented by a mean and a covariance function. So the only thing we need to provide is actually, or we need to store in our Kalman filter, if we think about it from an algorithmic point of view, is a mean and a covariance matrix. And we start with the mean and the covariance matrix of the belief, the state of the belief, or the parameters of the belief at the previous point in time, and evolve it into the new mean and new covariance matrix at the current point in time. So from t-1 to t, taking into account a Gaussian distribution for the motion noise and a Gaussian distribution for the observation noise. So all those things, everything stays Gaussian in here. So the main question is, how does t look like? So the the mean of the current belief and the covariance matrix of the current belief, relating that to all the Gaussian distributions of the previous belief. And that's the thing that we actually need to sit down and actually derive by hand. And this is very similar to the derivation that I just started with the convolution, showing that the convolution of those two Gaussians stay Gaussian by splitting this up into a product of Gaussians and then a marginalization operation, and then can show that I'm actually still staying in the Gaussian world. Very similar things happen if I say kind of how can I express the mean in the covariance matrix to derive this. So what the key toolbox that I need in order to derive the Kalman filter algorithm is the fact that the product of two Gaussians is still a Gaussian distribution. That if I take Gaussian distributions and transform them under linear transformations, they stay Gaussian distributions. The marginal and the conditional distribution of a Gaussian distribution stays a Gaussian. That's something important that we need to exploit. Then we need to be able to compute this mean and covariance of the marginal and the conditional distributions. So basically executing this, we need to take into account the convolution of two functions as Gaussian. We will use the matrix inversion lemma and a few other mathematical toolboxes that we know either from probability theory or from linear algebra. And then this leads us to a short algorithm. So I'm not showing this derivation here. This would be an exercise which would take a bit longer for that video here, but there is a lot of literature out there approaching it from the linear algebra point of view or from the probability theory point of view, and lets you derive the Kalman filter from scratch. Once you have done the exercise, you will come up with an algorithm that looks like this. So it's basically a 5-line algorithm. The first two lines, the lines 2 and 3 over here, tell us how the belief evolves given the motion command. So this is the prediction step over here, those two lines. So what happens, what is the input to the Kalman filter? Just to start maybe from the beginning, we have our previous mean and the uncertainty of our previous belief. So this is kind of the recursive belief. We add our control command and our current observation, and now want to evolve the state from t minus 1 to t. That means we need to compute a new mean and a new covariance matrix at time t. And we do this in 2 steps, first executing the prediction step and then executing the correction step. So in the prediction step, we need to evolve the mean and the covariance matrix. So we have our predicted mean, so the one with the bar is the predicted mean at time t, is our previous mean at time t minus 1, multiplying it with my matrix AT. So how does the state evolve if I don't do anything? This part over here, plus BT times UT. So how does the control command changes our state? And they both are added up. And this is kind of my linear model that I have in here. And based on this, I need to specify how the uncertainty evolves. And this is basically the effect on how does the first order error propagation, how does the uncertainty of a Gaussian distribution changes if it is squeezed through a linear function. And here I have the matrix AT multiplied with the uncertainty of the previous belief, AT transposed plus RT. So this is basically the additional noise that the motion adds to the current state. So this is my prediction step. And then at this point in time, I have my predicted belief computed in that way. And then I have my correction step, which is the 3 lines 4, 5, and 6 over here. And what basically happens here is that I'm computing a weighted sum of these 2 Gaussian distributions, or a weighted sum of the belief, basically the product of 2 Gaussian distributions. And the weighting factor is this KT over here. It's a so-called Kalman gain. And the Kalman gain tells me how much more do I trust the observation or how much more do I trust my belief. So it weights the prediction and the correction with each other. And we have with this term over here, it's basically a ratio taking into account the uncertainty of my observation, so sitting over here, and then some evolvement taking into account the my matrix CT, so the model which tells me how to map from the state space into the space of observations. And what basically happens in the end is then that in this term I take my new belief is my predicted mean, and then a correction term, and this correction term tells me how much does the observation actually changes my state. And what we do is we compute the difference between the actual observation that I've obtained and the predicted observation. So you kind of see that this term over here was basically the difference between the predicted belief and the predicted observation and the actual observation. So this term that was sitting in the exponent of my observation model, and multiplied with KT with the Kalman gain. And what the Kalman gain basically tells me here is how much does the difference between the actual observation and the predicted observation will change my state. And so I'm basically taking into account what's the difference between what I should observe and what I'm actually observing. And this difference is then mapped through the Kalman gain matrix into the state space and tells me how I need to update my predicted mean in order to take the correction through the observation into account. And then I need to also update not only the mean, I also need to update my covariance matrix so that through the observation, for example, my uncertainty typically decreases because I get a new observation, I get new information into the system, and therefore the uncertainty typically reduces through my observation. And this needs to be appropriately updated so that the uncertainty in my current belief is appropriately taken into account. And then the last step, I just kind of return the updated mean and the updated covariance matrix, now representing the Gaussian distribution at time t, so the updated belief. And then in the next step, this information would be fed in again here into the Kalman filter observation, taking then ut plus 1 and zt plus 1 into account. This would be then the next step, the next evolvement, given that we have a recursive state estimation algorithm over here. So maybe a small example in 1D. So consider that I have a belief and I perform a prediction. So I'm I'm predicting what the state will be at the next point in time. And let's say this Gaussian distribution, the red Gaussian distribution over here, is my prediction step. And then I get a new measurement, which is shown here or illustrated here by this green probability distribution. So I have a prediction and a measurement, and now need to combine those. And the combination of those is basically takes account which one weighs more depending on the uncertainty that I have. So a belief, a probability distribution which has a large covariance matrix will have a smaller impact on the final belief than one which is more peaked. You can nicely see it here in this illustration. The correction, which is shown here by the blue curve, is closer to the green curve, to the measurement, rather than the prediction. And the only reason for this is that I'm trusting my measurement more than my prediction, which can be seen on the variance of these two distributions. So the green curve has a smaller variance, so I trust it more, and therefore it will have a stronger impact after applying the correction step, ending up with this blue curve over here. And what you can see also here, the blue curve has a smaller uncertainty than the green curve, because it combines two Gaussian distributions, and so the uncertainty that we have here in the end is of the resulting Gaussian distribution is smaller than the two uncertainties we had here with the blue and the red curve over here. So we are actually getting more certain by adding this additional information into the game. In general, it is like this, that the prediction step increases my uncertainty because I add additional source of uncertainty to my gain. Given that I have a belief, and through the motion I kind of add more uncertainty to the belief. I have the uncertainty that I had before, plus the errors that I make through my control command. And then the measurement, through the measurement I get new information in there. I can reduce the uncertainty that I have by combining those two Gaussian distributions. So the prediction step increases the uncertainty, the measurement reduces the uncertainty, I mean, unless the motion is perfect, then we don't add any uncertainty, or if my measurement doesn't tell me anything, then I'm not reducing the uncertainty. But in most real-world situations, that will not be the case, and the motion will increase on the uncertainty, and the measurement will reduce the uncertainty that I have in here. But the important thing is, in the end, it's basically a weighted mean of these two beliefs, of these two state estimates. And the weight is computed based on the uncertainty of these distributions. So here the red one has a smaller weight than the green one over here. And this will then lead to the new belief. So we can take this a step further. So let's say we start now with the blue curve, which is now my belief at the next point in time, and I can perform a new prediction. So now the new prediction will be over here. So the system has moved into this direction, or evolved the state in the positive x-axis direction, but through this motion became more uncertain. And then we get a new observation in. This is the new observation that I get here. And this time the observation is not that good as the observation that I had before. This can change from observation to observation. And now I'm basically combining those distributions and get the yellow curve over here, which sits quite nicely in the middle between the two input curves. So everything that I do stays Gaussian. I'm basically combining the prediction and the correction into a new Gaussian belief, and I do this in a recursive fashion. And again, the two key assumptions that the Kalman filter does is, with Gaussian distributions, in my noise everything is Gaussian. So it means my prior belief is Gaussian, my observation model has Gaussian noise, and my motion model has Gaussian noise, and my motion and my observation model are linear. So they are linear models, and following these equations over here. And under these two assumptions, everything is good. Everything stays Gaussian. We know how to update our belief, and it's actually the optimal estimator, the best thing that we can do. The key question that, however, is there, what happens if this is not the case? So the assumptions, these two assumptions are actually very strong assumptions. That everything is Gaussian and that every model is linear are hard assumptions, especially the one with the linear motion observation models. This is basically violated all the time. You can still argue that a lot of sensors may have a Gaussian noise characteristic, or the Gaussian noise is a good approximation of the noise that we're actually obtaining. Most of the time you're actually kind of okay with this assumption, but the linear motion in linear observation is something which is in most situations not the case. You know this if you want to describe the motion of a vehicle, for example, even the 2D plane, or even worse, if you're in 3D, you have angular components often involved because the system is moving into some direction. So you will have sine and cosine functions popping up, and these functions are not linear functions. And as a result of this, they violate this assumption that the Kalman filter makes and cannot be applied in the plain vanilla Kalman filter. So, and as we do state estimation, often using the Euclidean space where we want to perform our estimations, then, and this involves also orientations and angles, this is something that we need to take into account. So we need to find ways for dealing with those nonlinear functions. So what happens if we have a nonlinear system? So most realistic systems, as I said, involve or will have systems which are nonlinear, and the question is how can we take this nonlinearity into account? So we need to get rid of those two expressions, and what happens if we are nonlinear? These functions are not linear functions anymore, so they turn into some new functions, the function g and the function h, one for the motion and one for the observation, which are not necessarily linear anymore, right? So the question is, first let us inspect what changes if we put in a different function g and a different function h, which are not linear anymore. Why is this a problem? Let's illustrate that. Okay, we can do this very nicely in a graphical way with this type of plot. So what we see down here is a Gaussian distribution, and this is our input. We want to transform this Gaussian distribution through a function. And let's say it is a linear function, so this function that we see over here. So, and this Gaussian distribution should be squeezed through this linear function and will give me a new Gaussian over here. Okay, so how does it look like? How can I illustrate this? I can take every point here on that function. I can move up here and basically deflect this ray onto the x-axis, and this is where this point will be mapped to for this new Gaussian. So the mean over here will be mapped to this new mean. This value over here will be mapped to this value over here. So all the probability mass which sits down here will be actually transformed through this function, ending up in this belief. And it's a very nice way for illustrating what happens with the function. And if I squeeze it through with the Gaussian distribution or any other distribution, if I squeeze it through, in this case, this linear function. So now I said, okay, we want to get rid of the assumption that everything is linear. That means we need to replace this function by a nonlinear function. Let's take a function which looks like this. So this is clearly a nonlinear function over here. So what we now need to do is we need to take every point here on that curve, or the probability math actually associated with it, and squeeze it through this nonlinear function over here. And what happens, the resulting distribution that we actually get is this black curve over here. We can clearly see that this black curve over here is not a Gaussian. So this input Gaussian is transformed into this black curve, which is clearly not a Gaussian distribution. So by using these nonlinear functions to evolve my state or perform my incorporate my observation, I'm actually leaving this Gaussian world assumption. We can still approximate this function here, this black function, by a Gaussian distribution, then we'll get the blue curve over here, but it's very obvious the case that this approximation is quite far away from the original function over here. So that's a problem that we have. So if we put in a Gaussian through this nonlinear function, then the output function will not be a Gaussian anymore. And as a result of this, the Kalman filter is not applicable anymore, because we are leaving this Gaussian world, and as soon as we leave this Gaussian world, the Kalman filter can't handle that anymore. So the key question is, what can we do to resolve this? So which tricks do we have in our kind of toolbox in order to modify the algorithm so that this information can be taken into account? Maybe not taken into account perfectly, maybe we still need to make some assumptions in here, but what can we do in order to deal with these nonlinearities, at least to some reasonable degree? And so what happens if we have this nonlinear function, what can we do in order to solve that? And the easiest trick to do is, let's say, okay, we know the function is nonlinear, but let's assume it to be linear and locally linearize it. So perform local linearizations. So I'm basically taking a point and at that point computing the first derivative of this function and fit a line through this nonlinear function at a specific point, at the linearization point, and treat it as a linear function depending how far I'm away from my linearization point. And this is something that we know as Taylor expansion, or a tool known as Taylor expansion that we are frequently using over here. So how does it work? What we need to do is, if we want to look to our prediction model over here, so we have our nonlinear function g with the parameters ut and xt minus 1. So what we need to do is, so here kind of xt minus 1, we need to take into account basically how far are we away with our new estimate given our previous belief. So we start by evaluating the function at the linearization point. Okay, so where are we? Our previous mean. And then we add to that a Jacobian of the first derivative of this function with respect to our state x, plus the question is how far am I away from my linearization point. So if you see this as my variable x, then basically how far am I away with my variable x from my mean, and this basically is a linearization of my prediction step. Same thing for the correction step that I have. If I have my function that depends on xt, this is my variable over here, I say I am at my linearization point, which is the predicted belief, because the best estimate that I have about the state before executing the correction. And then I compute the first derivative, or the Jacobian in the multidimensional case, of that function h with respect to xt, and then I have xt minus me prime, so how far is my variable away from my linearization point. So this turns into a linear function, so this is a constant, this is a constant, it's a linearization point, the y value over here, this is my linearization, so basically the slope of my linear function, and this basically tells me how far am I away from that linearization point. The same holds for the correction step as well as for the prediction steps. So, and just kind of as a short reminder, how does this first derivative look like in the multidimensional case? In the multidimensional case, it's not a single value, it's a matrix, a Jacobian, which is a non-square matrix. And so if you have an m-dimensional function, so in this case, this would be our state x, for example, the dimensionality of that state, m-dimensional, and then we have n different variables to which I'm going to derive it to. This would be the partial derivative of the first dimension of the function divided by the first variable, the first dimension of the function divided with respect to the second variable, and so on. And here in the individual columns we have that for whatever the mth dimension of my function g derived with respect to the first dimension of the parameter until the nth dimension of the parameter. It's basically a matrix filled with these partial derivatives. Again, we can also illustrate this. How can I use this for linearization? So if this is the function that I have in here, for example, here in this 2D case, this will lead to this plane, and basically I'm moving on that plane. This is kind of my two-dimensional function, which is a local linearization of the green function here at that point, or even shown over here. If this is my original function, I want to compute the linearization point in here, I basically get this blue plane, and I'm basically moving on that blue plane. What you can see also here is typically if I stay close enough to the linearization point, it can be a good approximation, but the further I move away from the linearization point, often the worse the approximation gets, especially with this blue curve down here. So this Jacobian is basically the generalization of the typical gradient of first derivative that you have in case we have multiple dimensions, so we leave the 1D world, which we nearly always do if we perform real-world state estimation with the Kalman filter. Okay, so as a result of this, these things turn into linear functions, right? Because It's just a constant, which is specified based on the linearization point, times my variable, how far I'm actually away. So let's see how this changes my overall setup that we had before. So this was our linear assumption. Then this was our nonlinear function, where we say, okay, this is kind of the result that we have. So what we are now doing, how does this local linearization work? So we choose the mean as our linearization point. So this is my linearization point. And then approximate this blue function by a linear function here shown in red. So this is my linearization point, my Taylor approximation, this red curve. And now I'm taking this Gaussian and transform it under this red curve, under this linearized function. Then I will actually get this red function over here. You should note that this red function is now a Gaussian distribution, because there's a linear function that was a Gaussian distribution. But of course, it cannot cover the nonlinearities of this blue function in an appropriate way. Again, if we would use the blue function, we would end up with this black curve over here. If we approximate or take this black curve and approximate it by a mean and a covariance or variance, it would add up with this blue function over here. And but the problem is this is something that we typically cannot do well. So the only thing we can do is we can perform this local linearization, compute this red curve over here, take the Gaussian, transfer it under the red curve, and then we'll end up having this red distribution over here. And there's even a mistake between the red and the blue curve. So we are far away from being perfect, but it's kind of the best thing that we can do in our current case, or the easiest thing we can do, let's say it that way. That's not the best thing we can do. There are better ways for performing those approximations, but it's kind of the standard way of doing this, performing a local linearization. The question is, how large is the mistake that we are actually doing? On what does it actually depend? And it actually depends on two quantities. On the first quantity is kind of how far is this red curve away from the blue curve? So how large is the mistake that I'm doing through the local linearization? If the blue and the red curve are very similar, also the approximation error can be assumed to be small. If they deviate strongly, then the approximation error will be large. And the second thing on what the approximation error depends on is actually the uncertainty, the input of that function over here. So, if the uncertainty is large, that means a lot of probability mass is distributed over the space here. And that means more probability mass will be mapped through the red function where I'm far away from the linearization point. And under the assumption that the further away I'm from the linearization point, the larger my approximation error gets, the larger the error that is generated through the transformation itself. So the smaller the uncertainty of this Gaussian distribution down here, the smaller the error of the output here. And we can actually illustrate this. Let's say we take a function which is a larger variance, so now more probability mass is spread out further away from the mean. That means I'm further away from the linearization point, and that means that this approximation error gets larger and larger over here. Okay? So we can see this, for example, by the difference between those two means, even if we just compute the difference between the two Gaussian, the red Gaussian and the blue Gaussian. If we, on the other hand, have a Gaussian with a smaller uncertainty in here, so if this is more peaked over here, then the error will be also smaller over here. So if this is more peaked, you can even see even the blue curve looks like more like a Gaussian distribution. It's not a Gaussian, but it's more like a Gaussian distribution. We can also see that the red and the blue curve come closer together. So the approximation error gets smaller. So this means that there are two things that impact the approximation error. First is how far am I away from the actual nonlinear function, and what's the uncertainty involved in this. So this is also one of the things that we will get to know about the Kalman filter. The smaller the uncertainty, the smaller the approximation error, and kind of the more similar my control model or my observation model is with respect to a linear world model, the better the performance of the Kalman filter. Okay, so let's have a look into the how does the linearized model looks like in terms of the motion model. So this was basically, what we're basically doing is we are taking the motion model as we specified it before, but now we replace this a times xt minus 1 plus b ut with my nonlinear function over here. So this is now my linearized function, my linearized motion. So I'm performing the linearization and then turn it into a Gaussian distribution. So the only thing which has changed compared to before, this is not this ax bu term plus bu term, but it's actually the linearized form using the Taylor approximation. And the same thing for my observation model. Instead of having here ct times xt, I now have my linearized observation model. So how's the mapping from the state space to the observation space in this linearized form? And that's shown over here. And what we now need to do is we need to take those linearization and put it into the Kalman filter algorithm, right? So we before had the Kalman filter algorithm, and now we need to turn it into the Kalman filter algorithm, which takes those linearized models into account. And luckily, there are very little changes I need to make to the Kalman filter algorithm to turn it to what we call the extended Kalman filter algorithm. Extended here because it extends the Kalman filter in the sense that we can use it with nonlinear models. And it stays very, very similar. The only thing that has changed are those two parts over here, which is I'm replacing the linear model with my nonlinear function for predicting the mean. So here I'm actually using this nonlinear function for making the prediction because I'm predicting just one single point. And this I can do without requiring my linearization. The same holds for the observation. So here I'm really using my function ht to map the predicted mean into what I'm expecting to observe in order to be able to compute the difference between what I'm actually observing, what I'm predicted to observe. And then what changes are the matrices, the matrix A and A transposed and C transposed, which are now replaced by G and H, which are the Jacobians of the of my motion and my observation. And the rest stays identical between the Kalman filter and the extended Kalman filter algorithm. So because I'm just using these linearized models, and so only the involved matrices in this linear function actually changed, and the rest will stay the same. What I also want to look into here, explain a bit, it is actually what happens with my correction step if I'm, for example, having a very good observation or very bad observation. And just kind of to give you a small hint what will change in here. So consider you have an observation which is perfect. So it is the perfect observation. It's the sensor with zero noise. So the question is, how can we see what happens to my state space in this situation? Okay, let's go a little bit into the details and explain what's going to happen. So what happens if we have the perfect sensor? A perfect sensor means the noise of the sensor is zero. That means we have our covariance matrix over here, and this covariance matrix is basically a matrix full of zeros, right? It's kind of the perfect sensor. Zero uncertainty associated to that. Okay, so that means this term drops away. So that what remains is here when we compute the Kalman gain, it's just the inverse of H transposed sigma bar HT transpose. So if I'm computing the inverse, I'm getting the inverse and I need to swap the order of the variables over here. Okay, so what happens if I'm inverting this term over here? I will receive these individual matrices inverted but kind of swapped. So I will have H transposed inverse sitting over here. So I will have H transposed times H transposed inverse. So those two variables will be gone because this identity matrix. And then the next term will be sigma bar, so the predicted uncertainty, and the predicted uncertainty inverse. Again, multiplied with each other, give me the identity matrix. So the only matrix which will remain will be HT inverse. So the Jacobian of my observation model inverted. This will be my new Kalman gain in this setup. Okay, now let's see what happens if we take this Kalman gain into account. If we take this Kalman gain into account, which is just kind of the observation function that we have in here, inverted, And what I'm actually doing, I kind of expand this, this bracket over here. So it is H inverse times ZT. So H inverse times ZT means I'm mapping from the state of observations into the state space. So I'm taking what I actually observed with the perfect sensor and map it into the state space. Okay? So this will give me, the product of these two terms, will give me where am I given that sensor reading? What's my state given that sensor reading? And then this term over here will be the inverse of H times H of the mean. So only the mean will remain. But then I have the mean minus the mean. So these terms will cancel each other out, will be 0. So the only thing which remains will be H inverse times ZT. And this will basically take the observation, map the observation into the state space 1 to 1. And the remaining state will be what the sensor told me. Which makes sense. If I have the perfect noise-free sensor, the prediction is completely cancelled out and I'm only taking the observation to determine my state space. And that's exactly what happens. Now we can turn it around and see the other thing. What happens actually if my sensor is the worst sensor ever, so it doesn't provide me any information? So we can see this as a covariance matrix which has infinity on the main diagonal. 0 information. Yeah, completely useless sensor. Okay, so that means I have this this term over here. This is basically a sum of something plus infinity. The sum of something finite plus infinity gives me infinity. So what remains is basically a covariance matrix which takes infinity on the main diagonal. And then I'm inverting this matrix, multiplied with some finite values. So basically the result will be 0 because I'm dividing by infinity. So whatever number I put in here, given this is this inverse, basically division, the Kalman gain will turn into 0. So the Kalman gain will be a matrix which is just filled with zeros. If I now go to the next step, say my current belief is my predicted belief plus the Kalman gain and something, and the Kalman gain is a 0 matrix, everything will cancel out. The only thing which remains is the current belief, a current mean is the predicted mean, which makes absolutely sense. If my sensor doesn't provide me any information, what I should do is I should trust my prediction. And that's exactly what happens. So if the sensor has infinite uncertainty, the Kalman gain will turn into 0, and then just the predicted belief will remain as my state estimate. And so as a result of this, we can see that these kind of two extreme cases can be very nicely explained what happens if you put the uncertainty of your sensor to 0 or to infinity. And you will either completely trust your observation or you will completely ignore the observation and basically just trust your prediction. And this is exactly what happens and what also makes sense in here. Okay, we can now use the Kalman, which we just introduced as a general framework over here for performing different things, such as localization. So this is just a kind of very small illustration example. In one of the next lectures, we will dive more into the details and provide you with the full approach to EKF-based localization, so you get an idea how that looks like. Or look into other state estimation tasks using the Kalman filter, but just kind of as a small illustration, what we've seen here. So what you see here, this gray line is the actual trajectory that the platform had been taken. And here we're 1, 2, 3, 4, 5, 6 landmarks in the environment. So things that the sensor can actually observe. So the system has an initial belief, let's say starts over here, and then things it moved over here, although in reality it took this movement. Then it got an observation over here, which is still seems to be, so based on the observation, the system will think it is actually here, because you have noise in your observation, and so the system thinks it's actually here, although it was kind of closer to the landmark based on the noise of the observation. Then it moves on, it probably was moving over here, moving straight, and then you get a new observation which actually drags the system kind of closer to the real belief. And then turning around, you always get your observations and update your belief. So this is basically the mean estimate of the trajectory that the system has taken based on the motion commands and the landmark observation that you actually get. And so if you run the EKF, this is kind of the motion that is actually executed, that is estimated. So here you can always see kind of the uncertainty of the prediction and the observation being integrated. So this is the uncertainty of the belief. And then you have the prediction and observation taken into account, combine that in a recursive state estimation fashion. So in the end, it's a weighted sum of the predictions and the observations. And this is kind of a small video example how that looks like in reality. You can, what you see here, these are landmarks, and if the thing is flashing up, you can see the actual observation. This is basically what the motion command tells you, so your prediction. You can see the system has a drift over here, and you can see here always kind of the estimate of the state, the estimate of the predicted state, and then taking into account the observation for correcting the belief, and the actual trajectory is driving, the system is driving here on that circle. And what you can see here with this blue line, which is the estimate of the extended Kalman filter, you can actually track the motion of the vehicle really well if you compare this kind of to just the motion that you would use, where you would end up with this pink trajectory over here. It's kind of a small example or a teaser how you can actually localize a system using an extended Kalman filter. So this brings me to the end of the lecture today, and just as a kind of short summary, what have you learned, or what should you have learned today? So the extended Kalman filter is a variant of the Kalman filter, and the Kalman filter itself was the base filter for the Gaussian linear case. And the EKF is one way to handle nonlinearities, and it does so by local linearizations, by computing Taylor expansions. And this is not the only way, this is just one way, kind of the straightforward, the most common way. But there are different variants on how to perform better approximations, such as the uncentered Kalman filter, where you go a different way than just using one linearization point and local linearizations. You may take more advanced approaches. And the EKF is still, or is one of the standard toolboxes that we can use today for state estimation, and it works well unless you either have extremely large uncertainties involved. So if you somewhere need to start with a prior belief, which is a more or less uniform distribution, or which is multimodal, then this can be problematic. Because then you're introducing large errors in your linearization, as we have seen. And the second thing is if your nonlinear models cannot be approximated well by a linearized function. This is also something when the Kalman filter is likely to fail. But as long as your models are not too far away from a linearized function, a linear function, or your uncertainties can be bounded, for example, by using high-quality sensors, the Kalman filter is a standard tool that we can use for recursive state estimation. So if you want to dive a little bit deeper into the topic, I recommend the probabilistic robotics book, especially chapter 3 and chapter 7 over here. And if you're interested in deriving the Kalman filter by manipulating Gaussian distributions, I recommend the article by Schoen and Lindstern, which you find freely on the net, where they go step by step through the derivation, whatever, 5-6 pages, something like this, ending up in deriving the Kalman filter. So you can actually, with the tools that I've shown you in the lecture, derive it by hand, although we have not explicitly done this derivation here. With this, I'm coming to the end of today. I hope you learned something about recursive state estimation and how a concrete realization of a recursive base filter looks like, namely the Kalman filter and extended Kalman filter, and now have tools at hand that you can actually use it for your own problems. In the remaining part of the lecture and the upcoming parts, we will look into examples how we can use the Kalman filter to actually solve one concrete state estimation problem, like localization or simultaneous localization and mapping, just as 2 examples. So thank you very much for your attention, and see you soon.